Hello and welcome to a new lesson on securing network traffic with SSH. In this lesson, we are going to learn how to protect our data using the Secure Shell Protocol or SSH. We will cover how it works, how to check its configuration, and how to use it to encrypt not just your terminal sessions, but other kinds of network traffic too. Back in the early days of Unix, networks were considered safe. Nobody worried much about attackers sniffing traffic. So, tools like Telnet, FTP, and rlogin sent everything, including passwords, in plain text. Fast forward to today, and we know better. Even your internal network isn't safe anymore. Attackers could be inside, or you might have a compromised device. That's where SSH comes in. SSH encrypts all communication between your system and the server. That means usernames, passwords, commands, everything is protected from eavesdropping. By default, SSH is installed on all Linux distros. First, let's check if SSH is already installed on your system. Most modern Linux distros include it by default. So let's execute which SSH. And as you can see, the SSH binary live inside /user/bin. That means we have SSH installed on our system. To check the status of SSH daemon, let's execute sudo systemctl status sshd. And as you can see, the service is enabled and it is running. SSH has two protocol versions, 1 and 2. Version 1 is old, insecure, and has known vulnerabilities. Version 2 is the standard today. If you are using modern distros like CentOS or Rocky or Red Hat, SSH Protocol 1 is not even supported anymore, so you don't need to do anything. It's already using Protocol 2. But if you are working on older systems or auditing existing servers, it's good to double check. To find out what version is in use, let's execute the following command. But first, let me go to the client machine to get its IP by executing IPA. And here is IP for client machine. I will just copy it. And I will go to our server machine and I will type SSH-VV, then the username vagrant and the IP of our client machine. Now let's press enter. And in the output, let's search for debug 1 remote protocol version. So I will scroll up. So here is the line debug 1 remote protocol version 2.0. That confirms that server is using protocol 2. If you ever find a server still using version 1 or protocol 1, you can fix that by editing the SSHD configuration file. So let me here provide any wrong password, or let me press Ctrl C so that I can exit back to the server without logging to the client SSH. Now let's check how we can configure protocol inside SSH configuration file. So let's execute sudo vi/etc ssh, then sshd_config, which is the main configuration file for SSH. And anywhere here you can provide the protocol you want. So here I will just add protocol 2, and don't forget that P is a capital letter. Then now let's save the file. And after saving the file, you need to restart the SSHD service to apply your modification. So let's execute systemctl restart SSHD. And let's check the status to ensure that everything is fine. And as you see, it's active and running since 6 seconds ago. Okay, now let's talk about SSH keys. SSH uses key pairs to handle encryption, one private, one public. These are usually stored in /etc/SSH. Let's take a look. So let's execute ls/etc SSH, then asterisk key asterisk. These default keys are generated during installation, and they work. But here is the problem. On some distributions, these keys might be reused, or they may have been created before the system had enough entropy, resulting in weak keys. So even on secure systems like Red Hat or CentOS, I like to delete the default keys and generate my own. That way, I know they are fresh and created with proper randomness. So let's see how we can do that. First, let's delete the default keys. So as a root, execute sudo rm-f, then /etc ssh asterisk key asterisk. Now press enter. If you executed the ls/etc, as you see, no such file or directories because we deleted the keys. Now regenerate them. The strongest and most common key type these days is ECDSA. We will start with that. So let's type sudo ssh-key gen, then -t and ECDSA, then -f, then /etc ssh, then ssh underscore host underscore ECDSA underscore key. Now press enter. When asked for a passphrase, we don't want one here because the system needs to access the key automatically. So I will just press enter and enter again, and our keys has been generated. Let's validate that. And as you can see, we have now the SSH underscore host underscore ECDSA key and its public key. You can repeat the same process for RSA and ED25519 if you want those two. Once you have generated your new keys, restart the SSH service. So I will do sudo systemctl restart sshd. And let's check the status. And it's active and running. There is no problem with SSHD service. Okay, now what happens when the key changes? When a client connects to the server, it checks the server's public key. If the key changes, you will get a warning like warning, remote host identification has changed. That's actually good. It protects you from man-in-the-middle attacks. If you know you changed the keys, remove the old entry. So where is the old entries saved on the system? It is saved under the .ssh known hosts file. So here you will find all entries. So if you know you changed the keys, you can double check this file or you can delete it if you want. Now let's talk about how to verify the fingerprint. So how do you know the new key is legit? When you generate a key, SSH gives you a fingerprint. You can check it again later by running this on the server. So here on the server machine, I will execute SSH key gen -l -f, then /etc SSH, then SSH underscore host underscore ECDSA underscore key dot pub. So here is the ECDSA fingerprint. You can then compare this with the one shown on the client when connecting. If it matches, it is safe to accept. So let's go to our client machine And from the client machine, I will connect to the server machine. So let's now execute SSH, vagrant at, then the server machine. Now press enter. Okay, now as you see from the output, we have the fingerprint SHA256IUXJ92, and this is for the ED25519. If we compared this with the output from our command, we will see that the fingerprint is different. But notice that here it gets a fingerprint of ED25519. But here our command, we got the fingerprint for ECDSA. So we will execute the same command again, but this time with SSH underscore host underscore ED25519 underscore key dot pub. So here is the fingerprint for the ED25519. It's IUX J92U, and if you compare this one with the fingerprint here, you will find that it is the same. So it is now safe to connect. So you will provide yes if you want to connect, or you will provide no if you don't want to connect. For me, I will just click Control C here because I don't want to connect to my server machine. Now let's go back to the server machine. And now here is where it gets interesting. SSH doesn't just encrypt terminal sessions. You can use it to encrypt any traffic, even for old protocols like Telnet FTP or SMTP that don't support encryption by default. Let's say you have a Telnet server running on a remote machine. You can create a secure tunnel for it. So now let's go to our client machine and let's execute this command SSH-4 for IP version 4, -F, -N capital, -L capital, then the local port 65023, then the localhost IP and the telnet port, then the username vagrant and our server machine. So that creates an encrypted tunnel from your machine on port 65023 to the remote telnet port 23, which is on the server machine. Now press enter and provide the vagrant password on server machine. It is by default vagrant. So it seems I didn't provide the right password, so I provided it again. And now we created an encrypted tunnel from our local machine, which is a client machine, to the remote telnet server, which is the server machine. To verify that, I can do netstate -ntlp. And as you can see now on my local machine, the port or the telnet port listen to 65023 through the SSH as a tunnel. So any communication on this port will be encrypted. So to recap our lesson, SSH is installed by default on most systems. Modern distros only support Protocol 2. It is smart to generate your own keys. SSH can tunnel and encrypt almost any kind of traffic, not just shell sessions. Thank you for watching and see you in the next lesson.